Hey everybody, this is Dr. Jacobs. Welcome to the last week of classes of actual content. So I would like to make the executive decision, and hopefully y'all are okay with this, to make some changes to our tentative course schedule, which is a right that I outlined. Let me look on our syllabus just to make sure. Yes, okay. It says I can change our syllabus at any time, and if it's for your better good, which I think this is. So this week, instead of having a long drawn out reading and a long drawn out lecture over a whole nother analysis, the changes that I'm going to make for this week is I'm going to do a little video review of everything that we've learned throughout the semester. And so hopefully you're okay with this. I'm going to give you the points that would have been for a lecture and a reading just by watching this video. Okay. So what I'm going to do is I'm going to go through that. And what I want you to do is while we're going through this, I want you to have a notebook or some paper with you and a pen or a pencil or some sort of writing utensil or some sort of study materials. And I'm going to try to review things with you. I don't want you to write in the comments the answers to the questions that I am providing you all, because I want you to use this as an opportunity to study everything that we've learned across the semester and try to gauge yourself where you are with all the materials for this class. So this will do a couple things. One, it'll help you remember all of the stuff that we've learned across the semester. And then two, this will also allow you to gauge where you are for the final. And three, it will actually give you more time to free up to do those calculation assignments that are going to be due this week as well. Okay, so in the very beginning of the semester, so hopefully you have your writing utensil ready and your notebooks and everything. Go ahead and grab those. Pause me if you have to. I'll still be here because I'm a video now. All right, so in the very beginning semester, week one, actually, I think technically it might have been week two, we went through chapter one. The purpose of the chapter one unit for this class was to prepare you for all the things that you're going to learn across the semester. Okay. So this is when we learned about data and statistics and the different kinds and things like that. So let's start from the beginning. I'm going to ask you questions. You're going to write down your answers. So if you got to pause me, write your answers down, and then check them with what I'm telling you the correct answers are. Okay. So let's do this study session for the final. So when we first started, I mentioned that statistics is all about data. What is data? So write your answer down. No cheating. You're only cheating yourself. So what is data? Data is information. So there's two major types of data that we learned about. What were those two major types of data? There is two major ones. There is qualitative data and there's quantitative data. What is qualitative data? Qualitative data is information that's represented by words. So then what is quantitative data? Quantitative data is information that's represented by numbers. All right, so in statistics, which type of data are we more concerned with? Which type of data do we use to do all of our analyses? So write down your answers. And it's kind of like Dora the Explorer, but I actually want you to write them down. So go ahead and write your answer for this. If you said quantitative data, you're right. So in statistics, we're primarily concerned with analyzing quantitative data. So in stats, there's two major branches. Write down what those two major branches of statistics are. Our two major branches of statistics are descriptive statistics and inferential statistics. All right, so then in the very beginning of class, we spent a few weeks going over descriptive statistics. What are those? Descriptive statistics are types of statistics where we try to describe our data set in one or a few numbers. So we didn't cover all of the different ones that there are out there, but we covered the majority of the ones that you will come in contact with. So descriptive statistics actually has three major branches or three different types of descriptive statistics. What are those major branches? Did you write down your answer? All right, so our first major branch of descriptive statistics was measures of central tendency. What was our second one? our second major branch of descriptive statistics. The second one was measures of variability. All right, and so then what's our third major branch of descriptive statistics? Our third major branch was measures of shape. All right, so each of those, we actually spent a week going over more information about those. One thing that we didn't kind of go back over is that when we have this quantitative data and we have these descriptive statistics, right? We have that branch of statistics, and then the next branch of statistics is inferential statistics. The goal with inferential statistics is to take a sample of participants and use what we find from that sample to make guesses about what's going on in the overall population, right? So we have these two major branches of statistics. And when we're doing these different things, and we learned that for the inferential statistics, we have the hypothesis testing steps that we take them through, and that we have a whole host of different inferential statistics. We have the one sample z-test, one sample t-test, independent samples t-test, dependent samples t-test, one way between groups ANOVA, Pearson product moment correlation, and linear regression. It's Friday. Okay. So we have those different types of inferential statistics. And so in order to do these different types of inferential statistics, in week one, we learned there's different research methods, types of things that we have to be able to apply in statistics so that we know what we're doing. All right. So one of those things is that we learned that all of the quantitative data that we have, it's not all created equal. It doesn't all provide us with the same amount of information. And in fact, we have 4 major types of levels of measurement. What was the mnemonic I told you all to remember to be able to remember the different levels of measurement? If you said NOIR, you're correct. NOIR. And each of those refer to one of the levels of measurement. And it's starting from the least precise, the lowest level of measurement that provides us the least amount of information, all the way up to the one that provides us the most. So the N in NOIR stands for nominal. This gives us the least amount of information. What is nominal data? So for nominal data, we see that we have a number that just represents some sort of phenomenon. So if I was asking you, what's your favorite color? And I said 1 equals red, 2 equals blue, 3 equals green, 4 equals fuchsia, 5 equals, I don't know, anything. Black. There we go. I couldn't think of colors for a minute. So we have all those. I didn't have to put those in order, right? They just represent some sort of phenomenon, right? I could have made 1 equals blue, 2 equals black, 3 equals red, 4 equals fuchsia. It didn't matter because there's no quantitative meaning that's associated with the numbers in nominal data. So then what does the O represent? The next level of measurement after nominal. If you said ordinal, you're correct. So what's difference? What is the difference then between nominal data and ordinal data? Well, unlike nominal data, ordinal data has a specific order to it. What ordinal data does not provide us, however, is what the distance in between each of our variables are. So if you are seeing people run a race, and we only know who got first, second, third, fourth, and fifth, we don't know if there's equal amount of time in between the person who got in first place and second place as there was from the second to third place, or third to fourth, or fourth to fifth. We have no idea if those intervals in between those numbers are equally spaced or not. And that's because all that ordinal data does is provide us an order. So then what is the I for? The I represented interval. And this is actually the one that is the most difficult to understand. In interval data, we do have those equally spaced numbers, but we have a 0 on the scale that is not meaningful. So what that means is either there's no 0 in the scale, like if we had 1 to 10 and there was no option for a 0, that would be interval level of measurement. If we had a size 0 shoe, it doesn't mean that there's not a shoe there. We're just saying that the 0 is a placeholder for whatever the size is. And so if you have a size 0 shoe, and then there's the same distance from a size 0 shoe to a size 1 as there is, we'll say these that are the same, pretend with me. So 0 to 1, 1 to 2, 2 to 3, that is interval data. Most textbooks, the way that they describe interval data is that it is some form of temperature. So either Fahrenheit, degrees Fahrenheit, or Celsius, right? Because 0 degree Fahrenheit does not mean that there is no temperature, right? And we know that because there's negative temperatures that we have. And then just like Celsius, 0 degrees Celsius does not mean lack of heat. It actually means where water freezes. There we go. So then after interval level of measurement, what is our most sophisticated type of level of measurement that provides us the most information? If you said ratio level of measurement, you are absolutely correct. And so the difference between interval level of measurement and ratio level of measurement is that the 0 in ratio means the lack of or nothing. So if I said I had 0 Topo Chicos to drink this week, that meant I didn't drink any of them. If I weighed 0 pounds, that means I don't weigh anything. I know that's really hard to think about sometimes because that's a very abstract type of thought. Because if you weigh 0 pounds, you don't exist, right? But that's because there's nothing there. So if you have 0 cups of sugar, how much sugar do you have? You don't have any cups of sugar. And so this became really important later on because a lot of the things that we do in this class, we can only do with data that's on an interval or ratio level of measurement. Okay. And so when we have data that falls on an interval or ratio level of measurement, we say that data is on a scale. So some other information that we learned about during week 1 was about something called reliability and validity. We learned that in order to do statistics, the measures that we use to collect our data, what is a measure again? You almost thought you got past without this one, right? So a measure is the tool that we use to convert information into numbers, right? So then what is measurement? Measurement is the process of turning information into numbers. And so when we do that, when we use a measure to turn information into numbers, we need that measure to be 2 things. We need that measure to be reliable, and we also need that measure to be valid. So a reliable measure means that it measures whatever construct you're trying to look at, it measures it consistently. Okay, so if you were trying to go on a diet, and I'm not saying people want to, right? But if you're going on a diet to try to, let's say, gain muscle mass, that's not going to help because we need to look at numbers. So let's say you're going on a diet to lose weight. And if you stepped on a scale and it said you weighed 205 pounds, you step off the scale and you step back on, it says you weigh 5 pounds. Why can't you use that scale? It's not consistently telling you the information that you need to know. So you don't know if it's reliable. You don't know if it's something that you can use or trust. And for a better example, I wish I would have thought of this one before I said that one. Like once my daughter got really, really sick, and we took her temperature and it said she had 105 temperature. We waited. One person got on the like my husband, I think, got on the phone with the doctor and we retook it. And then it said 98, right? Those are a really significant difference. And it was really frustrating at the time because we could tell that she wasn't doing very good. This fever came out of nowhere. And we, called the doctor. And meanwhile, we drove to Walmart because we were afraid we were going to need to take her into the emergency room. And we got the doctor on the phone, but we also got a new thermometer that was able to give us the accurate temperature for her. And thankfully, we didn't end up having to take her in to the hospital. But that was really scary, right? Because it wasn't giving us reliable information. Another thing that our measure must have so that we can use the data that we get from it is it must be valid. It must be actually measuring what it's supposed to measure. So if for your final exam, you're prepared, you're studying all of your things like we're doing right now for your final exam. And then when you got into the test and I asked questions about quantum physics, y'all not going to be happy with me, right? Then it's because that's not a valid measure of the information that we learned in this class over statistics. In that first chapter, we also learned about different basic research designs, which became really important once we got into inferential statistics. We learned about 3 different kinds. What were they? So if you said one was between group design, one was within group design, and one was match group design, you're correct. So you're going to want to go and review those different types of research design, especially if you didn't know which one was which. We also learned that there's several different types of sampling methods out there. What were 3 types of sampling methods that I taught you all about? So we learned about a convenience sample, a random sample, and snowball sampling. And so you'll want to review those as you move toward preparing for the final as well. So then after that first week, and there's other things that we studied, remembering that on these tests, I'm trying to see if you understand the material that we've learning, that we're not doing the calculations. I test you on whether or not you can do the calculations on those calculation assignments, because that whole week you have the opportunity to set up a Google Meet with me or come into my office hours to make sure that you're doing the right numbers. My goal for the calculation assignments is for people to get 100% on them. So make sure that you're using me as a resource on that if you need to. But for the exams, I'm more focused on, do you understand what we're actually doing? Because to me, that's the more important part. After you get out of this class, you're going to be using software to do most of this stuff. And so I do want you to still be able to do the calculations, because that helps you understand what we're trying to find with each of them. But really, I don't think people should be penalized for math calculations, which is why I give you the whole week to do it and the opportunity to come in and check your answers with me if you want. And so that first week after we got through our introductory chapter, we went over measures of central tendency. What are measures of central tendency? Oh man, I got off topic. It is a Friday for sure. What I was saying with the unit learning objectives, that's what I would use to make sure that you're studying for the exam. We're going through some of these now, but we're not going to be able to cover everything. So then we moved on to measures of central tendency. What were those? If you say measures of central tendency, tell us, try to tell us the center of our data set in one or a few numbers. You're absolutely correct. And that's what we do. What are the types of measures of central tendency that we learned in this class? We learned about the mean, the median, and the mode. And so when we did that, sorry, I had to drink some of my sparkling water. When we learned about that, we learned that not all data can be used, or we can't find the mean, median, mode of every different types of data that are out there. And we did a few different little learning activities and worksheets while we worked through some of the problem solving that goes along with that. And so what you'll want to do is make sure that you go back and review, okay, so what types of data can we find the mean for? If you're not sure, right, there's only 2 of them that we can use for it. And so you're going to want to go back and review that. We learned that if we have an outlier in our data set, we can't do the mean, because the mean is really heavily influenced by outliers. And we did a little activity with that online as well. And so if I wanted, I could provide a data set for you all and then have you tell me and select which types of measures of central tendency you could do with that data set. So not only do you have to know what each of the things are, you have to be able to practically look at a data set and say, yeah, okay, I could do this, or I can't do this. And that is because I want you to be able to see, like when you're out in the real world, that if you are presented with some data and someone's like, hey, can you kind of find the mean for this? And if it's data that's on a nominal or ordinal level of measurement, you're going to know that you can't do it because we don't have those equal distance in between the numbers. Our intervals are not equally spaced. And so after that, we moved on to measures of variability. What kind of information do measures of variability tell us? Measures of variability tell us how spread out our data set is. And so there's different ways that we learned about this. We learned about the least complicated form of it first, which was the range. There was 2 different types of range. What were they? We had both the inclusive and exclusive range, so you'll want to review those and what the difference between the 2 of them are. And then we learned some other ones that were a little bit more difficult. We learned about standard deviation, variance, and mean absolute deviation. You're also, while you're preparing for your final exam, you're also going to want to be able to review each of the symbols that we've learned across. So hopefully you've been keeping up on that symbol sheet that I've been telling you all to construct each week, so that you can really know those symbols really quickly. So with measures of variability, we had the range like we just spoke about, but we also had the variance, standard deviation, and mean absolute deviation that we learned together, because what the goal for those were, and what scientists were trying to figure out to do, was how can we tell about how far each of our x's are away from the center of our data set, our mean. And so we went through a really long activity with really trying to understand what these measures of variability were trying to tell us. So if we wanted to know what the average distance each of our X values were away from the mean, how would we go about that? What would you need to do first? If you said that you needed to figure out the distance by taking the X minus the mean, because that literally tells you how far away from the mean each X value is, that's absolutely correct. And so you had to figure that out first. And once you have those distances, logically, what would be the next step? So if you wanted to find the average distance that X values were away from the mean, you would take, like logically, you would add all of them up and divide by the sample size, right? Unfortunately, we found that when we add up all those X minus the means, also known as our deviation score, when we did that, when we sum all those deviation scores together, that value always is going to equal 0. There are some circumstances where if you're rounding some of the numbers like we do in this class, remember, we always round to 2 places past the decimal unless I tell you otherwise. The problem is, if you round like that, then you might get like 0.02 or 0.03 or something really close, or negative 0.04. And that's only because you rounded. But if you didn't do any rounding, that number will always equal 0. And so scientists were like, oh, okay, so what do we got to do next, right? Like if you can't do that, what can we do to each of those deviation scores so we can eliminate those negatives and still try to get an approximation of what the average distance these X values are away from the mean? And so when they did that, there's 2 different options, and these 2 different methods actually became popular at the same time, but one became more prominent than the other. So one thing that you could do to your deviation scores that would eliminate the negatives and keep the proportions of those original X values with relation to the mean and the other X values was you could just take the absolute value. Because we remember with our deviation scores, negative values only tell us that the X value is to the left of the mean, and the positive values just tell us that those X values are to the right of the mean. They actually don't tell us anything about the distance. They just say which side it's on. And so the absolute value makes sense because then it eliminates the information that is making it cancel out all the positive ones, because we know the mean is the very center of our data set that kind of balances around it. And so when we did that, we were on the path to calculate something called the mean absolute deviation. The symbol for that is my favorite symbol in the whole world, and it is capital MAD, capital MAD. And it makes me mad because science decided to not go with this as the prominent measure of variability, even though it makes more sense and it's exactly what it was trying to account for. And so with MAD, you take the absolute value of all those deviation scores, you add all of them up and divide by the sample size. So you literally have the average distance each of the X values are away from the mean. So, but that's not what science went with. Science decided to go with variance and standard deviation. So instead of taking the absolute value of those deviation scores, when you're going to calculate variance and standard deviation, what they do is they square those deviation scores. And so when they square those deviation scores, it eliminates the negative, because if we square a negative number, a negative times a negative is a positive. And so what they did is they squared them. And then they took those squared deviation scores and they add all of those up to get a number called the sum of squares. And then to get variance, all they do in the general idea of variance is divide the sum of squares by the sample size. Technically, it would be the population size because the formulas are a little different. And then, but the problem with that is that doesn't accurately represent how far each X is away from the mean, right? Why is that? It's because we squared those deviation scores, so it's not in the same form. And so what they wanted to do then is they wanted to take the inverse of squaring with whatever the variance was, so to try to get it back into the standard form. So what is the opposite of squaring something? The opposite of squaring something is taking the taking the square root, right? So to do that, what they did is they took the variance, they took the square root of the variance, and that's how they get the standard deviation. What they were trying to do is take back when they squared all this deviation scores earlier in the calculation. And although it does a pretty good job getting it close to what it was, it actually doesn't do it completely. And so the metaphor I used for that is if you've ever said something to somebody that you didn't mean, and then you try to take it back and they may even apologize, but once you say something, you can never actually take that back. And that's what it is with standard deviation. They try to take back the squaring by taking the square root of the final number, but it didn't take away all of what they had done. There were still some lingering results from doing that. So after we learned those, we moved on to measures of shape, where we learned about skew and kurtosis. We also learned about different shapes data can have. And we learned about distribution. So what was a distribution again? So we learned that a distribution is just how frequently each X value occurs in our data set. And whether or not we visually display these distributions still exist. And so in measures of shape, that information that we're getting from that is what shape would our distribution have if we plotted it out. And we learned several different types. We learned about positively skewed data, negatively skewed data, normal distribution. We learned about the J shape. We learned about uniform distribution, which is also sometimes called rectangular distribution shape. And we learned about those with the primary goal of later on wanting to know that we're going to deal mostly with normally distributed data, or data that kind of follows the shape of that normal curve, which was the next chapter afterward. And so when we were dealing with those measures of shape, we learned that there's two major types of skew. What were they? They are positive skew and negative skew. And then we learned that there were different types of kurtosis. What is kurtosis again? Kurtosis is how pointy our distribution is if we're putting it out onto a histogram. So with that, we have leptokurtic data, which means that our data set is more pointy than our normal curve. We had mesokurtic data, and that is kurtosis that is the same as the normal curve. And then we have my favorite one. It's a platykurtic, and that is when the distribution is flatter than the normal curve. And I like that one because it makes me think of Perry the platypus from Phineas and Ferb. And so I kind of joke with people that if you don't get this one, it's really sad because it's got a flat bill. The distribution's flat like a platypus bill. And so we moved on to using our understanding that when we build these distributions and things, which we learned to do, we learned to build quite a few different ones. Actually, what were the kinds that we learned to create in class? So we learned to build frequency distribution tables first, and there's three major types of frequency distribution tables that we learned. What were they? So we learned an ungrouped frequency distribution table, a grouped frequency distribution table, and a cumulative frequency distribution table. And when we were doing it, we learned to create them with specific formatting rules that you should know, and go back and review if you don't remember what all those formatting rules were. And then we learned that if we had a really wide range of data, that sometimes we have to create group frequency distribution tables. And the way that we do that is we have to figure out how wide each of our groups are going to be. So each of the groups are called class intervals. That's the groups of ranges of data that we have. We learned that we had to figure out what the inclusive range of those are, and that's our class interval width. And we learned that we need about 10 to 20 class intervals when we're creating a group frequency or a group frequency distribution table. So if I wanted to do a group frequency distribution table of grades, I might have a class interval. I might have quite a few different class intervals per se. Let's say at the bottom, because we know formatting wise that we have the highest values at the top of a frequency distribution table and the lower values at the bottom. So I might have 0 to 9. Then I might have 10 to 19, and 20 to 29, and 30 to 39, and so forth through the whole data set. And so the class intervals are those individual groups all the way up. The class interval range, or the class interval width, however, is the inclusive range of each of the individual class intervals. So for example, 0 to 9 is one class interval. The inclusive range of that is what? If you said 10, you're correct, right? So 9 minus 0 plus 1 is 10. And that's because it's including all the values that are in that range. We learned that our class intervals needed to be mutually exclusive, which means that one X value can only fit into one class interval. We learned that we need 10 to 20 of those class intervals in our group frequency distribution table. We learned that that there's a certain way that you can kind of problem solve to get those 10 to 20 class intervals and the class interval width. And you can go back and review the materials from that week if you don't remember. Then we also learned about the cumulative frequency distribution table, and that's where we learned about how to do percentile ranks and percentile points and how to create those. And then the last visual display of our distributions that we learned to create was histograms. And so histograms are kind of my favorite because it allows us to actually see kind of the shape of the distribution, which allows us to visually inspect if it looks like it's a normal curve or not. And so we use all this understanding because when we moved on to the next unit where we learned about the normal curve, one thing that I really wanted to hit home with you all was that there is data underneath our normal curve. And so we used the normal curve to solve some problems, some area under the curve problems, which were a little tricky, but they allowed us to visualize when we could use this in the real world. So specifically, we examined if we were trying to do course placements, how we could use scores to figure that out. And so after that, we moved on to a very short probability unit where we learned about two major theorems of probability. So you want to know some of the terminology from that unit, like probability, what the symbols are, for all of the units. You're going to want to know what independence events are, what it means to be mutually exclusive with probability itself, because we see that terminology across different units. And so you're also going to want to know the two major theorems of probability. What were those? I've now officially run out of water. We learned about the addition theorem of probability and the multiplication theorem of probability. We learned that they have nicknames and that there's very specific functions that we use those theorems of probability for. And so that unit was all about helping you understand about what probability means, so that when we moved on into the next unit where we learned about the hypothesis testing steps and we see a p-value, what that information is trying to tell us. All right, so then we got out of statistics boot camp and moved into inferential statistics, and we started learning about the hypothesis testing steps. What were those hypothesis testing steps in order? Pause me and write this down because this is very, very important information. All right, so the hypothesis testing steps, what's our first step? Our first step is to determine which statistical analysis we're going to use. And we do that. We have different questions that we have to ask ourselves when we're trying to determine which statistical analysis we're going to use. This is actually one of my course learning objectives that you're able to determine based off of the research question or the data set or what we're trying to find, what statistical analysis you would use. So I would make sure while you're preparing that you know when you use every single one that we learned so far. So with this, there's things you ask yourself. The very first question you need to ask yourself is, what's the goal of the analysis? So are you trying to see if there's a relationship? Are you trying to see if there's significant differences? Are you trying to make predictions, right? Then you also need to know what type of basic research design. If you're comparing groups, how many groups are you comparing? Is your dependent variable on a scale? So those are things that help you determine which statistical analysis you're going to use. And we learned several different ones. We learned the one sample z-test, the one sample t-test, the independent samples t-test, the dependent samples t-test, the one way between groups ANOVA, the Pearson product moment correlation, and our last one that we learned was linear regression. So you should know when we would use all 7 of those while you're preparing for the final. So then our second step after determining our statistical analysis includes writing our research in null hypotheses in symbols and in words. And we learned that we can write our hypotheses directionally or non-directionally. The way that we write our research hypothesis. So if we write our research hypothesis directionally, we also have to do that with our null hypothesis. But if we choose to write them non-directionally, we have to do whatever we do to one, we have to do the other. As a researcher, the hypothesis that we want to be the accurate explanation with what's going on with our data set is our research hypothesis, which is symbolized by H sub 1 and then a colon. The other type of hypothesis, the null hypothesis, is the complete opposite of our research hypothesis. And its symbol is H sub 0, because 0 means null or nothing. And so we learned to write those both in symbols and words. We knew there's subtle variations depending on which statistical analysis that we're using, but they generally follow pretty similar format depend on what we're doing though. So after we do that, step 3 then is to do what? Is to check our assumptions. And so assumptions, if we remember, are the characteristics that our data set have to meet in order for us to run whatever analysis we're doing. A lot of the assumptions kind of repeat across different statistical analyses. And so for that, I don't actually care that you know which assumptions go with which analysis, because if you're in the real world, hopefully you save your notes from this class and you can just go and look, and then you can do whatever you need to do. And then so with it though, we had several different types of assumptions that we learned about. We learned about normality. We learned about homogeneity of variance. We learned about our data set can't have outliers. We learned that for all these different types that we're learning, that there needs to be our dependent variable, if we have one, needs to be on a scale. If we're doing correlation, then both variables need to be on a scale. If we're using linear regression, like we learned, both variables need to be on a scale. I'm trying to think, we had random selection as one of our assumptions. That means we randomly selected our sample from the population. And so I may have left some of them out, but you should be able to tell me what each of these assumptions are. And if we meet or violate the assumption, given whatever data I provide you. If we meet the assumption, that means that's cool. We don't have to move on to see if there's another way that we can still do the analysis. We just meet it and move on. However, if we violate an assumption, in some situations when we violate our assumption, that's not necessarily a deal breaker. And if we meet other conditions, we can still do it anyway. So for example, if we violate, which almost gets violated every time, that we randomly selected our sample, that we didn't randomly select our sample because we used either convenience or snowball sample. If we violate that, that's okay. We can still do the analysis anyway, as long as we don't try to generalize the results from our sample back to the population we are interested in studying, right? So that means that whatever analysis it is robust to the violation of the assumption, as long as we don't try to generalize it back to the population. All right, so if we define robust, we say that analysis is robust to a violation. So for example, the independent samples t-test is robust to the violation of normality. So if you don't meet the assumption of normality, you can still do it anyways, as long as your sample size is at least 30. All right, so after checking your assumptions, after you're good to go with that, you move on to step 4 where you calculate your test statistic. We learned that there's different test statistic formulas depending on which statistical analysis you're running. And we had the formulas for each of them. And so after you calculate your test statistic, then you move on to step 5, which is finding your critical values. We also learned that finding your critical values depends on what test statistic and analysis that you're using. And there's different things that go into making that decision. There are several different tables that I provided throughout the semester in PDF form in our modules. So that's, I would save those because a lot of the critical value tables that are actually out there have errors in them. And I created these ones myself using a programmed Excel to do the calculations so that I know that they're accurate. So after we find the critical values, then step 6, what do? Then we're going to make a decision. And when we make our decision, there's only 2 decisions that we can make. Either we retain our null hypothesis or we reject our null hypothesis. And so what we do then is we draw out our normal curve. We put a line under our normal curve. Typically, unless you're doing a ANOVA, but for most analyses, you're going to put a 0 in the middle on that number line. Then you're going to put your critical value next. So let's say we have a positive critical value. We'll draw that on our normal curve to the right of the 0 because that's where our positive numbers go. And we'd label critical value and then put whatever the value number is there. Where the section is in our normal curve, that's by the 0. We would put retain the null hypothesis, and then beyond our critical value, we'd put reject the null hypothesis. After that, then we would label our test statistic value that we calculated in step 4. We'd put whatever test statistic. So if we did a a t-test of some sort, we would put t equals whatever test statistic value the number is. And then where that falls on the line, if it goes beyond the critical value, then we reject our null hypothesis, which means we have statistically significant results. However, if it doesn't move beyond our critical value, then we retain our null hypothesis and we don't have significant results. So when we go to write our results and symbols, we learn that there's a typical format for doing that. We have whatever test statistic value, we write it. So if we're doing a t-test of some sort, we put t, and then after t, we put in parentheses the degrees of freedom. So whatever number we calculated for that equals, then we put the test statistic value. So that's that number that we calculated in step 4. If we have not significant results, we'd have comma, p, which is p-value. If you don't know what a p-value is, then you're going to need to know that for sure. And if it's not significant results, we have equals n dot s dot, which means not significant. If we do have significant results, we'd have p is less than our alpha level, which is 0.05 for this class, unless I've said otherwise. So, and then if you have statistically significant results in step 6, you would move on to step 7 to conduct some form of follow-up analysis, depending on what statistical analysis you did. So step 7. So say that we had statistically significant results in step 6. In step 7, we'd do some form of effect size known as Cohen's d. So I don't care that you know how to calculate Cohen's d on our test. What I do want you to know is, what is that telling us? What does effect size tell us that we don't learn about, that we don't learn from having statistically significant results in step 6? And that's a good question. What does effect size tell us? Effect size tells us how meaningful our differences are. So like in step 6, all we're doing is saying, so if we're doing independent samples t-test, remember we do that when we're comparing two groups that use a between group research design with a dependent variable that's on a scale. And that all we're finding out in step 6 is if our means are significantly different from one another. What that tells us is that we think that those differences didn't occur due to chance. We think that there's actually a difference there. So step 7, if we do Cohen's d, then we're trying to see how big those differences are. You also, again, need to know when we use each of our statistical analyses. We remember we do a one sample z-test. When do we do a one sample z-test? We do a one sample z-test when we want to compare the mean of a sample to the mean of a population, and we know the population standard deviation. When do we use a one sample t-test? We use a one sample t-test when we want to compare one sample mean to a population mean, and we don't know the population standard deviation. When do we use an independent samples t-test? We use an independent samples t-test when we want to compare the means of two samples. That uses a between groups research design, which means we have different participants in each group, and our dependent variable is on a scale, which means our dependent variable is either measured on an interval or ratio level of measurement. When do we use a dependent samples t-test? We use a dependent samples t-test when we want to compare the differences between two sample means, and it's either using a within group design or a match group design, and our dependent variable is on a scale. So let's talk about that a little bit. So with a within group design is when we have the same participants in both groups. So for example, when you took your pre-test for this class, and then this week you're going to take your post-test, you have taken both of those. You are in both the pre-test condition and the post-test condition. And I actually will run a dependent samples t-test, which is why I have that as an assignment. Sometimes people are like, why do you have a little post-test and then we have to go and take the final exam? And that's for a couple of reasons. One, it helps me evaluate my own teaching, so I can see how effective my teaching methods are in the class. But that also helps you gauge on how well you're doing in the class, because it's closed book. And although you can see your score on it, that score actually isn't going in your grade, because I'll go in and put participation points in for it later. Okay, so, and then a match group design, remember that's a very complicated type of design, so you may want to go back and review it, because that would be a really long drawn out explanation just for this quick review that we're doing. So then when do we use a one-way between groups ANOVA? We use a one-way between groups ANOVA when we're comparing the differences between 3 or more groups. and there's different participants in each level of the independent variable. What's the symbol for levels of independent variable again? If you said K, you are correct. Lowercase italicized K, and that's just the number of groups you're comparing. That's what a level is. And then when do we use a Pearson product moment correlation? We use a Pearson product moment correlation where we're trying to see if there's a relationship between two variables, both of them on a scale, and both the variables come from the same participant. So if I want to see if there was a correlation between the amount of coffee that my participants have drunk and how much sleep they got the night before, I would ask every single participant, how much coffee have you had? How much sleep did you get last night? And then I would put this into the formula to see what kind of relationship there was. Remembering that correlation, the values go from -1 to +1, where a -1 means there's a perfect indirect correlation, and a +1 means there's a perfect direct correlation with it. And then that brings us to the last analysis that we learned a little bit about last week, which was linear regression. When do we use linear regression? We use linear regression when we want to make predictions about a y variable based off of an x value. And so in order to do that, we remember that we learned that in order to do it, they have to be correlated, highly correlated with one another so that we can make those predictions. And we learned that those predictions are not going to be perfect. So I think we've gone through a lot of the information that you need to know. Make sure you're using those unit learning objectives to help study. You also want to know what a p-value is. You want to know what alpha levels tell us. You'll want to know how to make the decisions if we're going to reject or retain or null hypotheses. And you're going to want to use those unit learning objectives to make a study guide. And I am very excited. I'm sure y'all are very excited to be moving towards summer, where the weather is hopefully very lovely, and you can also have some picnics and go on hikes and things too. If you have any questions, please hit me up this week. This is the last week that I'm going to be having office hours because during finals week, the faculty schedules change a little bit. So if you have any questions, please let me know. If you want to meet in office hours, or if you're coming in person, you can just show up. That's fine too. Or if you need a Google Meet instead because you're studying from far away, that's okay too. All right. I really glad to have you all in here. I know it's really hard to take a class on statistics online, but y'all made it. All right. Have a great week.